Hello. Hello. Okay. So hello everyone. Welcome to PW. Good evening once again. Now I think audio problem is resolved. Okay. Now it is not on the mute. Till now we have already completed very important part, that is flip-flops. Today's class is the most important class for both CS, EC or EE or IN student. Okay. For all of the branches it is very important. Why? Because it has two parts and both the parts are equally important. One is the asynchronous counters and other one is the synchronous counters. Almost 80% of the chances that question are going to be framed from synchronous or asynchronous counters. Is it okay? Is the audio and video now? Is the audio and video now perfect? Can you please let me know by writing in the comment section, beta ji, is the now audio and video everything is perfect? Great. Now see, so we have already covered registers. Okay. Now you know how to solve the questions based on the registers. Today I am going to discuss about the counters, type of counters, application of counters, ripple counters, and then we will move towards the synchronous counters as well. All of you are ready? Great, sir. Is the audio, video, everything is okay now? Is the audio, video, everything is okay now? Please let me know by writing in the comment section, beta ji. Great. Now please observe first about the counters. So you can just ask your friends to come faster as today's topic is very important. Now please observe basics of counters. If we talk about counter in a single line, counter is nothing but it is just a frequency divider circuit and it is designed to count number of circuit cycles through which it operates. Basically, counter counts clock pulses. Counter count clock pulses as the name counter. So it counts clock pulses. Now please observe here. It is a type of sequential circuit which is used to count number of clock pulses. The sequence of state may follows the sequence of binary or other sequence of the state. It means suppose on the first clock we are getting 0 0 0, then on application of the next clock in the counter we may get 0 0 1, in the next we get 0 0 0 0 1 0. So if we are getting the binary sequence, binary of 0 1 2 3 4 5 and so on, then the counter is called as a binary counter. If it counts in some other sequences, then it is called as a non-binary counter. Is it okay? Yes, sir. So the counter which follows binary number sequence are called binary counter. If the counter follows binary sequence, it doesn't matter whether up or down, then only we called it as a binary counter. Is it okay, beta ji? Is it okay? Great. Now please observe here. An n-bit binary counter consists of n number of flip-flops. N-bit binary counter consists of n number of flip-flops. It means if we have 4-bit binary counter, then 4-bit binary counter may contains 4 flip-flops. To count from 0 to 2 to the power n whole minus 1. Suppose if we have a 4-bit binary counter, then it contains 4 flip-flop and it counts from 0 to 15. Is it okay? In the same way, for n-bit binary counter consists of n flip-flops and it counts from 0 to 2 to the power n whole minus 1. We all know about the range of unsigned numbers. Okay. Now in every count, binary number is called binary number is called state of the counter. In every count, the binary that we got, let us suppose on the application of clock we are getting 0001. So this 0001 is called as a state of the counter. Is it okay? Yes, sir. Hence, the counter counting in terms of n bit, the counter counting in terms of n bit with n flip flop has 2 to the power n number of different state, because 000 is also a state. So from 0 to 2 to the power n whole minus 1. Is it okay? Let us suppose we have a 4 bit. So 0 to 15. 0 is also a state. So total become 16 states. Is it okay? So total become 2 to the power n state. With the n flip flop, maximum possible states are 2 to the power n only. That is, maximum possible states are 2 to the power n only. How many of you able to understand up to this part? Just an introduction. I will let you know everything in detail. Just an introduction. Now the term mod count. What is mod count? The number of different states in counting sequence is called mod count. In short, you can say number of different states obtained in a counter is called mod count of the counter. With n flip flops, counter will have 2 to the power n number of different states. Then the counter will be called as mod 2 to the power n counter. Let us suppose we have a 3. Let us suppose we have a 3 flip flop. So maximum possible states are 2 to the power n. Maximum possible states are 2 to the power n. It means 2 to the power 3. Okay. Number of different state, if 2 to the power 3, then the counter will be called as a mod 8 counter, that is 2 to the power 3. Is it okay? But this is only for binary counter. This line is only true for binary counter. Is it okay? Yes, sir. Please write down in the comment section, beta. In general, if m is the total number of states and n is the total number of flip flops, if m is the total number of states and n is the total number of flip flops, okay, yes sir, then m is less than or equals to 2 to the power n. Always remember, where m is number of states and n is number of flip flops. Suppose if we want to design a mod 4 counter, then it can be designed by 2 flip flop. If we want to design mod 5 counter, then we need 3 flip flop, because for 5 state we must need 3 flip flop. Is it okay? There are some unused state as well, and that is not a binary counter anymore. How many of you able to understand up to this part, beta ji? Great. Now if we talk about the types of counters, then counters are asynchronous counters or synchronous counters. Asynchronous counters and synchronous counters. What is the difference between asynchronous counters and synchronous counters? Please observe the difference between asynchronous and synchronous counter. The one and most important difference is, in synchronous counters, all flip flops are triggered at same time with the same clock. However, in case of asynchronous counters, different flip flops are triggered with the different clocks. In short, I can say in synchronous counters, all flip flops are connected with the same clock. However, in case of asynchronous counters, different flip flops are connected with a different clock pulse. So different flip flops are connected with a different clock pulse. Is it okay? Can you please respond in the comment section? Can anyone please respond in the comment section, beta, that everything is going perfect? Great. Now please observe one more line. It is slower. We are talking about asynchronous. Asynchronous are slower because of the propagation delay. However, synchronous counters are faster. Asynchronous counters only operate in a fixed sequence as up counter or a down counter. However, synchronous counter can be designed for any count sequence. Large number of states can be designed easily in case of asynchronous counters. However, the large number of states increases the complexities in the design. Ripple up and down counters are the examples of asynchronous counters. However, ring counter and twisted counters are the example of a synchronous counters. Now let's try to understand how they will design and how they will behave, how they are going to work. Yes, beta, it is why does each state, because counter is nothing but it is a frequency divider circuit, and we are going to learn the same thing what you have asked. Okay, now please observe beta ji. First application of the counter is frequency dividing, counting the number of clock pulses, mostly used in analog to digital converter, which is one of the very essential part of your digital electronics, and in digital clocks. Is it okay? Now let's come back to the asynchronous counters first. We know that two types of counters are there. One is called as a synchronous counter, one is called as a asynchronous counter. The basic difference is in asynchronous counters, different clock pulses are applied to different flip-flop. However, in synchronous counters, only single clock is applied to all flip-flop. It means in synchronous counter, all the flip-flops will operate at the same time. However, in case of asynchronous counters, the flip-flops may operate differently in a single clock pulse because different flip-flops are connected to the different clock pulse. So let us first understand synchronous counter. Asynchronous counter. Let us first understand asynchronous counter. In an asynchronous counter, ripple counter we can use. Okay, so to design up and down counter first, so that we will have a little bit idea about the asynchronous counter. So in an asynchronous counter, I am using ripple counter. Okay, yes sir. Now ripple counters. In a ripple counter, this is very important and that we must need to note down. Rest you can download the PDF, but from here you must need to note down. Sir, after digital can we have electrical machine? That we will let you know. Please observe here. All the flip-flops in a ripple counter are operating in a toggle mode. First and most important is all the flip-flops in a ripple counter are operating in a toggle mode. Different flip-flops are connected with a different clock pulses. Input clock is applied to only one flip-flop and that will act as least significant bit. Very important. Input clock pulse in case of a ripple counter is connected with only one flip-flop. That will act as a least significant bit. The clock of next flip-flop is the input. The clock input to next flip-flop. The clock input to next of the flip-flop is the output of previous flip-flop, and so on. Same thing goes on. Is it okay? Yes, sir. So the clock input to next flip-flop is the output of previous flip-flop. Now let us first try to understand the 3-bit ripple counter as positive edge triggered up counter. Please write down 3-bit ripple counter as positive edge triggered up counter. Okay. Now please see, for 3-bit how many number of flip-flops are needed? 3 flip-flops are needed. So I am using 3 flip-flop. Now either we can use JK flip-flop or we can use T flip-flop, because in ripple counter flip-flops are operating in a toggle mode. So JK flip-flop will operate in a toggle mode when both J and K are 1, or T flip-flop will operate in a toggle mode if T is equals to 1. So I am going to use a T flip-flop. Please observe here. I am going to use T flip-flop. Input clock is connected with only one flip-flop and that will act as a least significant bit. Please observe very carefully, beta ji. Input clock is connected to only one flip-flop and that will act as a least significant bit. So here I am using the input clock. Is it okay? Yes, sir. Input clock is connected to only one flip-flop and that will act as a least significant bit. Is it okay? Yes, sir. In ripple counter, flip-flops are operating in a toggle mode. Yes, sir. Now, it's a up counter for a positive edge triggered clock. Positive edge triggered means whenever the clock changes its level from low to high, only during the transition the clock will appear and the circuit get activated. Okay. Yes, sir. So when this will go 0 to 1, this will become your flip-flop T1, next significant bit, and the output of next is the input of most significant input clock to the most significant bit. So now I am hoping all of you know how to mark MSB and LSB in case of a ripple counter. In a ripple counter, flip-flops are operating in a toggle mode. Yes, sir. We can see that all the flip-flops T1, T2 or T0 are in a toggle mode. Base clock is applied to only one flip-flop. Input clock is applied to only one flip-flop, and that will act as a least significant bit. The output of LSB is becoming clock to the next significant bit, and so on till most significant bit. How many of you able to understand up to this part? I need your response, Bitaji. I need your response. Please let me know by writing in the comment section. Yes, sir. Can I say Q0 toggles only when Q0 toggles only when clock changes, or I can write Q0 toggles on each positive edge triggered clock Q0 toggles on each positive edge triggered clock. Can I say this? Yes, sir, because T0 is equals to 1. And we all know about the truth table of the T flip-flop. If T0 is equals to 1, then as soon as clock appear, the output get changes, toggles. Is it okay? Yes, sir. So the output here get toggles on every positive edge triggered clock. It means Q0 toggles on every positive edge triggered clock. However, if we observe Q1 toggles only when, see, the clock appear onto the flip-flop 1 and the clock onto the flip-flop 1 is Q0. This is the symbol of positive edge triggered. So it means when the Q0 changes from 0 to 1, and the time when Q0 is changing from 0 to 1, at the same time in the latch of T flip-flop, Q0 is changing from 1 to 0. So that indicates Q1 toggles only when Q0 bar will go from 0 to 1. That is Q0 will go from 1 to 0. How many of you able to understand? Great. Now please observe same for the Q2. When Q2 toggles, T2 is equals to 1 as per the flip-flop truth table. We all know flip-flop truth table. T flip-flop truth table. Hoping all of you remember the T flip-flop truth table. So in case of T flip-flop, if we have a clock T Qn plus 1, then until unless there is no clock, irrespective of T, it will remain in Qn. When the clock appears, then for 0 it holds and for 1 it toggles. How many of you remember this? Yes, sir. So it indicates with t is equals to 1, the output next state get toggled, but only when the clock appears. So the clock to t1 is this. Whenever q0 bar will go from 0 to 1, it means q0 will go from 1 to 0. Only at that transition instant of q0 1 to 0 will make the clock appear onto the flip-flop 1, and therefore flip-flop 1 output gets toggled. Is it okay? Yes, sir. Now if you observe q2, so the clock to q2 is q1 complement, that indicates it's a symbol of positive S triggered. So that indicate q2 toggles only when q1 bar will go from 0 to 1, because it's a positive S triggered symbol. When q1 bar will go from 0 to 1, q1 will go from 1 to 0. It means q2 toggles only when q1 bar will go from 0 to 1. That is, q1 will go from 1 to 0. How many of you able to understand? Sir, it is very difficult. What do you want to say? We are just able to understand that what you have represented here, but we are unable to understand what is going on. No issue. You need to note down this. Okay? You need to note down this. Let me explain with the help of timing diagram. So allow me to draw the timing diagram. Up to this part, whatever represented, hoping 10% you will be able to understand. Only 10%. Whatever indicated, you will be able to see that. That's all about 10%. Now let's talk to timing diagram first to understand. So let's have timing diagram. Okay. Now please observe, beta ji. Neglect TPDFF neglect TPDFF, that is propagation delay of flip-flops. Okay. So neglect propagation delay of flip-flops. We will discuss about the propagation delays as well, but for presently I am neglecting propagation delay. Okay. Now please observe here, we have a clock. So I am representing the clock first like this. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm just extending the clock levels wherever the clock changes its level from 0 to 1. So I'm just extending to understand the behavior of the different flip-flops and the different states wherever the clock changes its level from 0 to 1. So this is your first clock, second clock, third clock, fourth clock, fifth clock, sixth clock, seventh clock, eighth clock, and ninth clock. The clock would appear onto the flip-flop only during the transition of the clock from 0 to 1. Please read this once more. Please read once more. Please read once more at your own speed. Please read once more at your own speed. Very fast. Okay, great. So Q0 toggles on every positive edge triggered clock. What does it means? It means if we have Q0, please observe here, this is the clock. Then Q0 toggles on every positive edge triggered clock. Since the initial state is not given, so we will consider the initial state onto the flip-flop latches as 0, 0, 0. So if Q0 is initially 0, then as soon as the clock appears, Q0 changes its level and it will become high. At this instant, it will become high because we are neglecting the propagation delay of the flip-flop. If we consider propagation delay of the flip-flop, it will change its state after a small span of time. Is it okay? But I'm neglecting propagation delay. So at the instant when the clock is changing its level from 0 to 1, you can consider Q0 changes level from 0 to 1. Now, it will remain same until unless again the clock would appear onto the flip-flop, because this is a positive edge triggered clock. Only during the transition the circuit get activated and based upon the input output get toggled. Now when there is no transition of the clock from 0 to 1, there is no clock onto the flip-flop, and until unless there is no clock onto the flip-flop, flip-flop output will remain in the previous state. Previous state means it will remain high until unless again the clock would appear, it will remain in its state. Again we are getting a clock at this point. Soon as the clock changes level from 0 to 1, again your T0 get activated and its output get toggled. Toggled means if it was 1, it will become 0. Now on every positive edge triggered clock pulse, Q0 toggles, because when the clock appear with the T is equals to 1, flip-flop output gets toggled. Is it okay? Yes, sir. So this waveform we get for the output Q0. Now please observe here. Hoping all of you able to understand. Great. Now please observe here. We have T1 is equals to 1. But until unless there is a clock appear on this flip-flop, the output will not change. The output will change only when a clock appeared onto the flip-flop and the clock is positive as triggered. It means during the transition of Q0 bar from 0 to 1. When Q0 bar is in transition from 0 to 1, at that time Q0 is in transition from 1 to 0. So it means whenever it changes 1 to 0, whenever Q0 changes 1 to 0, at that instant the clock would appear onto the flip-flop 1. Initially we have considered the flip-flop 1 as well, flip-flop 1 as a 0 level. Okay, yes sir, all we are considering Q0, Q1 and Q2 0 level. Now until unless there is no clock onto Q1, the Q1 state will not change. So there is no clock on Q1 because the clock on Q1 is Q0, and whenever Q0 changes from 1 to 0, Q0 bar changes from 0 to 1, Q0 bar changes from 0 to 1, at the same time Q0 changes from 1 to 0, so 1 to 0. Here we are observing the clock appear. As soon as the clock appear, the flip-flop get toggled because T is equals to 1. then it will remain high until unless again the clock would appear onto the flip-flop. Soon as the clock appear, as the clock is Q0 bar, which is changing from 0 to 1, it indicates Q0 changing 1 to 0, it toggles. So it toggles on whenever Q0 changes from 1 to 0. Now what is the clock to Q2? Flip-flop Q2, we know T2 is high, but the output get toggled only when the clock appear. If there is no clock, it doesn't matter what is the value of T, output will not change. Output will only change when the clock appear. And since it's a S triggered, so whenever the clock is in transition, positive S triggered from 0 to 1, only at that instant the flip-flop output get changes. So now please observe here, T2 flip-flop will have a clock Q1 complement. So whenever Q1 complement changes from 1 to 0, at this during this transition, your Q1 changes from, whenever this is changing from 0 to 1, Q1 changes from 1 to 0. So you have to observe where Q1 is changing from 1 to 0. Q1 is changing from 1 to 0 only at these two positions. Here it is changing from 0 to 1, low level to high level to low level. Now please observe. So sir, Q2 will remain same until unless Q2 will remain in the low state until unless there would be a clock onto the flip-flop 2. At this instant when the clock appear, because of the zero propagation delay, output get changes at the same time, and it will remain in the same state until unless there is another clock comes. At this point the clock come to the flip-flop T2, and now the state get toggled and become low. How many of you able to understand the timing diagram at the different outputs of the 3-bit ripple counter? What is the current state of syllabus covered on this channel? So beta ji, we have started a flip-flop sequential circuit day before yesterday, and today we are on to the counter. Okay. Now how many of you able to understand beta ji? Great sir. Now please observe about the states. We have Q2, Q1, Q0. Okay. Yes sir. Q2, Q1, Q0. Q2, Q1, Q0. In terms of Q2, Q1, Q0, with a Q2 as a MSB and Q0 as a LSB, in the different, on application of the clock pulse, what are the different states we are getting? What are the different states we are getting? Please observe beta ji. In terms of Q2, Q1, Q0, what are the different states we are getting? Before applying any clock, the state initially we have assumed 0, 0, 0. On application of the clock, Q2 will remain at low level, Q1 will remain at low level, and Q0 will be at high level. So Q0 will be at high level. So we will get 0, 0, 1. How many of you able to understand? Then on second clock pulse, on application of second clock pulse, Q0 will become low, Q1 will become high, and Q2 remain low. So we will get 0, 1, 0. On application of third clock pulse, Q0 high, Q1 high, Q2 low, low, high, high. Then this is low, this one is high, so we will get 1, 0, 0. Here, sir, we are getting Q0 high, Q1 low, Q2 high. If you observe, on application of sixth clock pulse, we are getting 1, 1, 0. In the same way, on application of seventh clock pulse, we are getting 1, 1, 1. On application of 8th clock pulse, we are getting 0, 0, 0. On application of 9th clock pulse, again we are getting 0, 0, 1. So how many different states are there? Different states. We start counting the state after applying the clock pulses. Very important line. Always start counting the different state after applying clock pulse. Is it okay? Yes, sir. So after applying clock pulse, how many different state? Sir, binary of 1, 2, 3, 4, 5, 6, 7, 8. On to 8th condition, we are getting 0, 0, 0. So 0, 0, 0 is also a state. We will never consider the initial. We always consider after the states after applying the clock pulses. So how many number of different states are there? Sir, we can observe here 8 different states are there. So 8 different states are there. We can say this as a mod 8 counter. So this counter is said to be a mod 8 counter. How many of you able to understand? Please let me know by writing in the comment section, beta ji. Great, sir. Now please observe. Very important. If we talk about clock frequency, then clock frequency is 1 upon time period of the clock. In ripple counter, if you observe the time period of the clock, then from this to this, repetition get started. So this is your time period of the clock. Is it okay? Yes, sir. If we observe the output Q0 and we wanted to find out the frequency of output Q0, then output Q0 you can observe high and then again becoming high at this position. So in between we have 2 TCLK, 2 time period of the clock. So if 2 time period of the clock, you can write 1 upon 2 TCLK and 1 upon TCLK is FCLK. So one can write, sir, FCLK by 2. How many of you able to understand up to this part? If you observe Q1 will have from the same point, if we observe total number of clock pulses are, this is the same point, na? 4 TCLK. So that indicate output Q1 frequency, Q1 or Q1 complement, both will have the same frequency. Output Q1 or Q1 complement will have the frequency 1 upon 4 TCLK, which can be represented as FCLK by 4. And similarly, F2, F of Q2 will become, now please observe 001, this state, and 001 again we are getting here. So the repetition get started from 001 to 001, total 8 TCLK. So one can say 1 upon 8 TCLK. So this will become FCLK by 8. Suppose instead of using 3, if we are going to use 4 flip-flop, then that will become FCLK by 16, FCLK by 32 and so on, if you are going to increase the number of bits and number of flip-flops. Is it okay? It is called as binary up counter. Why the name binary up counter? Because from 000 it counts the binary of 1, 2, 3, 4 on the up side of the numbers. So this is what we call up counter. So this is a binary 3-bit binary ripple counter, up counter with a positive S triggered clock. How many of you able to understand, beta ji? Let's talk once again with the truth table and the number of states. Please observe once again, beta ji. Sir, we have clock Q2, Q1, Q0. We have clock Q2, Q1, Q0. Please observe here. Onto the 0th clock pulse, we have a state 000. Now first, second, third, fourth, fifth, sixth, seventh, 8th, 9th, 10th. We are interested to find out the states in these different clock pulses. Okay? Yes, sir. These clock pulses numberings are in terms of base clock pulse, which is applied only on one flip-flop, and that will act as a least significant bit. So we have observed that Q0 toggles on every positive S triggered clock pulse. Yes, sir. So Q0 toggles. If it is 0 on application of the clock, it will become 1. If it is 1, it will become 0. So on every clock pulse, your Q0 toggles. Q1 toggles, from the circuit we have observed, Q1 toggles only when Q0 bar will go from 0 to 1, that is Q0 will go from 1 to 0. So Q0 will go from 1 to 0. You have to observe where Q0 is going from 1 to 0. The positions where Q0 is changing from 1 to 0, only at that duration clock appear. So please observe here, 0 to 1. So clock is not appearing, it will remain 0. It will remain 0. Yes, sir. It becomes high only when Q0 changes from 1 to 0. So here Q0 is in transition from 1 to 0, so it toggles. 0, so toggles to 1. 0 to 1, it will remain same. 1 to 0, it toggles. 0 to 1, it will remain same. 1 to 0, it toggles. 0 to 1, it will remain same. 1 to 0, it toggles. So how many of you able to understand that Q1 toggles whenever Q0 changes from 1 to 0? In the same way, Q2 toggles only when Q1 changes from 1 to 0. So you have to observe Q1 changes from 1 to 0. It remains same until unless there is no change in Q1 because there is no clock pulse appeared onto the flip-flop 2. Now at this transition of 1 to 0 of Q1, clock appear and it toggles becomes logic 1. How many of you able to understand up to this part? How many number of different states are there? The total number of different states, we always count the state after applying the clock pulse. So how many number of different states? We have 8 different states. So this is your mod 8 up counter. How many of you able to understand, beta ji? They may ask you what kind of questions are possible in a ripple counter. They may ask you to identify the output waveform. They may ask you output frequency at any of the output port. Always remember the Q2 and Q2 bar will have same, Q1 and Q1 bar will have same frequency. Only they are their levels are inverted to each other. Is it okay? Yes, sir. One more type of questions they may ask. They can ask you identify the mod of the counter, nature of the counter, mod it up or a down counter. You have to identify like these. Okay. We are able to understand up to the part that if this is FCLK, we are getting either of the outputs as FCLK by 2. So in the next we are getting again divided by 2, so FCLK by 4. How many of you able to understand, beta ji? And then we are getting FCLK by 8. Hoping all of you able to understand up to this part. Great. Now let's have a discussion once again onto the same 3-bit up counter but with a negative edge triggered clock. And I'm going to consider the propagation delay also in this particular case. So be attentive, please. I need your focus to understand this. Okay? Yes, sir. Great. So please observe once again. How many of you able to understand? Please let me know by writing in the comment section, beta ji. How many of you able to understand? Please let me know by writing in the comment section, beta ji. Great. Now 3-bit up counter, ripple up counter, 3-bit up counter as a 3-bit ripple counter as a up counter with negative edge triggered. Is it okay? Previously we have discussed positive edge triggered, and now I am going to discuss about the negative edge triggered. Okay? Yes, sir. So ripple counter you can design either by using T flip-flop or by JK flip-flop. If you are going to design with a T flip-flop, then T is equals to 1. If you are going to design with a JK flip-flop, then J and K both equal to 1. Yes, sir. So T Q Q bar, T Q Q bar. Only one flip-flop is connected with a base clock pulse, and that will act as a least significant bit. The output of least significant bit flip-flop will become clock to the next significant flip-flop. Is it okay? Yes, sir. In that way you can identify the next significant bits. Is it okay? Yes, sir. So now you can easily observe the different significant bits on the counter. In ripple counter, flip-flops always operates in a toggle mode. Up to this part everything is okay. For 3-bit we need 3 flip-flop. Great, sir. We all remember about the T flip-flop truth table. So we have clock T, Qn plus 1. Okay. Yes, sir. Until unless there is no clock, irrespective of Qn, we have the data same as the previous data. The next state is same as the previous state. Only when there is a clock, then depending upon t input 0 or 1, the next state will be available. So if t is equals to 0 and a clock appear, then t flip flop holds, 3 flip flops holds, and when 1 appear, t flip flop toggles. So it toggles only when t is equals to 1 and a clock appear. We have already applied t is equals to 1, but until unless there is no clock, there is no change in the data. Is it okay? Yes, sir. Now please observe, the first thing that you can observe here is Q naught toggles on each clock pulse, each negative H triggered clock. Yes, sir. Second, Q1 toggles. We have a negative S triggering. Q1 toggles. What is the meaning of negative S triggering, beta ji? Negative S triggering means whenever the clock changes its level from 1 to 0. Is it okay? Yes, sir. Now, this is the symbol of negative S triggering. Negative S triggered means during the transition of the clock from high to low. Negative S triggering, high to low, positive S triggering, low to high transition. So, the clock of Q1 is basically output Q0. So, Q1 toggles only when Q0 changes its level from 1 to 0. Negative S triggering. Q2 toggles only when Q1 changes its level from 1 to 0. How many of you are able to understand? So Q1 toggles only when Q0 changes from 1 to 0. Similarly, Q2 toggles only when Q1 changes from 1 to 0. How many of you are able to understand this? Great, sir. Can we see the truth table now? Yes, sir. Let's have a discussion of the different states first. Then we will see the timing diagram as well. Okay. Yes, sir. So please observe, beta ji. Sir, we can see clock Q2, Q1 and Q0. So on to the 0th clock pulse, we are considering that all the flip-flops are resetted. 1, 2, 3, 4, 5, 6, 7, 8, 9. If we observe the output states, the states of the different flip-flops at different or under different clock pulses, then, sir, Q0 toggles on every negative S triggered clock. So if it is 0, it toggles to 1, 0, 1, 0, 1, 0, 1, 0, 1. However, Q1 toggles only when Q0 changes its level from 0 to 1, 0 to 1 to 0, 1 to 0. So it toggles only when it will changes its level from 1 to 0. How many of you able to understand, beta ji? Now Q2 toggles only when Q1 changes its level from 0 to 1. So that indicate we have 8 different states, and the states are always counted after applying the clock pulse. So how many total number of different state? 8 states. So this is your mod 8 up counter. There is no doubt in this. How many of you able to understand? Great, sir. Let's try to understand with the help of timing diagram once again. Let's try to understand with the help of timing diagram. Okay. I'm going to show you the propagation delay and the effect of propagation delay. What is the demerit of asynchronous counter? All we are going to have with this. But before introducing the propagation delay, let me draw once again with a neglecting propagation delay. Okay. So if we neglect propagation delay, because I'm going to draw in the same, so please observe everyone. On neglecting propagation delay, first I am drawing on neglecting the propagation delay. So 1, 2, 3, 4. Okay. So how many number of clock pulses here? We have 1, 2, 3, 4, 5, 6, 7, 8, 9. Sufficient. Now please observe 1, 2, 3, 4, 5, 6, 7, 8, 9. So first I have drawn the clock. Is it okay? Now please observe, we all know how to design a clock for a counter. We have studied in the logic gates where we have completed the stable multi-vibrator. Okay. So if we have a clock, then clock appear onto the flip-flops whenever the clock level changes from high to low, because it is a negative S triggered negative S triggered clock. So negative S triggered clock, Q naught toggles on every negative S triggered clock. If we draw for Q naught considering initially Q naught 0, then Q naught toggles on every negative S triggered clock. How many of you able to understand, beta ji? Q naught toggles on every negative S triggered clock. Hoping all of you able to understand up to this part. Yes, sir. If we talk about Q1, then Q0, whenever Q0 changes from 1 to 0, because the clock onto the flip-flop 1 is Q0. So whenever Q0 changes from 1 to 0. So these are the position where Q0 changes from 1 to 0. 1 to 0, not 0 to 1, only the transition from 1 to 0, because it's a negative S trigger. So Q1, if we draw the timing diagram for Q1 on neglecting propagation delay, we get this timing diagram. How many of you able to understand? The output of Q1 get toggles whenever Q0 changes from 1 to 0. And if we talk about Q2, then Q2, whenever Q1 changes from 1 to 0, because for the flip-flop 2, the clock is Q1. So whenever Q1 changes from 1 to 0, then only the clock appear. So whenever Q1 changes from 1 to 0. How many of you able to understand up to this part? Please let me know by writing in the comment section, beta ji. Great. Someone is asking continuously, sir, when the electrical machine will get started. Beta ji, I will start electrical machine. You need to wait a little bit. First, the basic subjects will get completed, and then we will start up machines as well. So you have to follow the series, especially for those who are in electrical branches, and for CS or ECE student, also you have to follow the same series. Presently, digital is going on. The next subject will come, and so on. Okay, it totally depends upon your demands, beta ji, and everything is connected. And how we will measure the demand as per the views. Is it okay? So it all depends upon your demand, and the demand will be observed with the views. Okay. So now please observe Q2. If we talk about Q2, so Q2 is changing its level here. Presently, I have neglected the propagation delay, but in an actual case, there is a propagation delay. Yes, sir. So let each flip-flop have TPD-FF, propagation delay. If we talk about flip-flop with a propagation delay, then what happened? If the propagation delay is present, then instead of getting this white line, we will get this green line. Please observe very carefully. Instead of getting this white line, we will get this green line. At this transition from 1 to 0, clock appear onto the flip-flop 1. But as soon as the clock appear, there would be no change in the output. It would take some time to get the output stabilized. Is it okay? Yes, sir. So it is taking a time of TPDFF. After TPDFF, the output is changing. Is it okay? So post application of the clock, propagation delay, TPDFF, your output changes its level. So output changes its level post propagation delay of TPDFF. Instead of getting this white line, we will get this green line. So now the green line indicates the clock is shifted here. The green line indicates now the clocks are this. How many of this is just to understand Bitaji, and it's very important. Now the clock is not appearing here. So definitely instead of getting this white line for Q1, we will get, instead of getting this white line for Q1, the clock appearing at these positions, which is indicated by green dotted line. Okay. So clocks are appearing here. So when the clock appear, then it would take further TPDFF time to respond and to change the output. Is it okay? Yes, sir. So output will not change here. Instead of here, output is changing onto the positions indicated by the blue line. How many of you able to understand, Bitaji? Great, sir. So now the clock onto the flip-flop 2 would appear when Q2 changes from 1 to 0. So instead of clock appearing here, the clock is now actually appearing onto the pink positions. So if the clock appearing onto the pink position, instead of having this white line of Q2 as output, we will get this as a output. How many of you now able to understand? Because of the propagation delay, we are getting this timing diagram. I am just making the white line with a lighted background so that confusion further get reduces. Okay. Yes, sir. Now, if you observe this timing diagram, we are facing an issue. What is the issue? Please observe, Bitaji. In terms of Q2, Q1 and Q0, before applying the first clock, we have the state 0, 0, 0. After applying first clock pulse, we have the state again 0, 0, 0 for a small portion of time, that is TPDFF. That is TPDFF. Yes, sir. And post TPDFF, we get the state 0, 0, 1. Post TPDFF, we get the state 0, 0, 1. If you observe next, then instead of having the output, we are getting here the change is of 2 TPDFF. It is visible to all of you? 2 TPDFF. So what it indicates? It indicates how many levels we are getting. After applying the clock pulse, we want the state to be a binary of 2, that is 0, 1, 0. But what we are getting, for TPD-FF time post application of the second clock pulse, we are getting 0, 0, 0, 0, 1, and then after 1 TPD-FF, we are getting 0, 0, 1, and then we are getting 0, 1, 0. So we are getting some of the states which are undesired. On application of the clock, we want if the present state is 0, 0, next state would become 0, 0, 1. But instead of 0, 0, 1, just after the clock, it would remain 0, 0. We can observe on the second clock what happened. Instead of getting 0, 0, 0, 1, 0, we are getting 0, 0, 1, again 0, 0, 1, and then we are getting 0, 1, 0. In the same way, if you observe Betaji, you will find that some of the undesired states are coming. Like here, you can observe 0, 1, 0. So 0, 1, 0 we are getting. 0, 1, 0 we are getting. Then on after the third clock pulse, we are getting 0, 1, 1. How many of you able to see this? Now please observe. If you observe on application of the fourth clock pulse, what happened? This is high, and this is low. So we are getting 0, 1, 1. Then after TPD-FF time, this will become low, this is high, and this will become low, 0, 1, 0. And then after TPD-FF time, we are getting, again we are getting here 0, 0, 0. We are getting 0, 0, 0. And then we are getting 1, 0, 0. So you can see that there is a transition of the state, and during the transition we are getting some unwanted states. Is it okay? We want on application of the clock this state, but instead of getting this state, we are getting first this state, then other state, then other state, because of the propagation delay of the different flip-flops. This is what we call decoding error. So asynchronous counters suffers from decoding error. First thing, even if we want to remove the decoding error by using strobing, it's very simple, that outputs are being transferred through the AND gate. So if the outputs are transferred through the AND gate, and AND gate get enabled when all the flip-flops get operated. So the decoding issue get removed, but the delay increases. The delay increases means, if you observe, in order for the satisfactory operation of this particular counter, we must need to apply a clock pulse having time period more than 3 TPD-FF. Because if it is less than 3 TPD-FF, you will not get the valid state even just before the end of the clock. Is it okay? Yes, sir. So for satisfactory operation of the asynchronous flip-flop, your time period needed must be greater than n TPD-FF, greater than or equals to n TPD-FF. So it indicates that for asynchronous counters, TCLK, time period of the clock, must be greater than or equals to n TPD-FF, where n is the number of flip-flops. Is it okay? Or number of bits, you can say. Number of flip-flops here, number of flip-flops. How many of you able to understand up to this part? So that makes the circuit sluggish. This makes the counter sluggish, and also a decoding error is present. Decoding error is present. This is what we called decoding error. Hoping all of you able to understand the timing diagram, delay and decoding error now in a best possible way. Great. Let's have a discussion towards one more. Can you design a 3-bit down counter with a negative S triggered clock? Can you design a 3-bit down counter with a negative S triggered clock or with a positive S triggered clock? With a positive S triggered clock. Yes, sir. How to design a 3-bit down counter? Sir, we have one flip-flop, another flip-flop, another flip-flop. We must use T or JK. So T, Q, Q bar, T, Q, Q bar, T, Q, Q bar. Only one flip-flop in which base clock is applied, and that will act as a least significant bit. So this will become 0. In ripple counter, flip-flops are operating in a toggle mode. The output of this flip-flop will become input to the next flip-flop. How many of you are able to understand? Yes, sir. The output of this flip-flop will become clock to the next flip-flop. Now we all know this will become 1 and this will become the most significant bit, MSB. Now we all can see that Q0 toggles on every positive S triggered clock pulse. However, Q1 toggles, I'm just writing here, Q0 toggles on each clock. Q1 toggles only when positive clock appear onto the flip-flop 1. Positive clock means the clock when the level transition of the clock is from low to high. So low to high, it means Q0 will go from 0 to 1. When Q0 will go from 0 to 1. That is I am interested for the down counter, na? Wait, betaji, I am interested for the down counter. Kindly made a correction. I have made a up counter here. This is a down counter. Kindly do the correction here, betaji. This is the down counter. Now please observe. Down counter indicates Q1 will toggle only when Q0 bar will go from Q0 will go from 0 to 1. In the same way, Q2 toggles only when Q1 will go from 0 to 1. Kindly do this correction, beta ji. I am designing a down counter now. If we connect Q0 bar with a positive S triggered, it will become up. Okay, so kindly do this. Toggle only when Q0 will go from 0 to 1. In the same way, if we talk about Q2 toggles only when Q1 will go from 0 to 1. So now you know that both Q0 or Q1 when goes from 0 to 1, the other two flip-flops are going to be toggled because they have already T is equals to 1. Only they are waiting for a clock. As soon as the clock appear, the output get toggled. Is it okay? Yes, sir. If we talk about a state table, then we have clock Q2, Q1, Q0. We have clock Q2, Q1, Q0. Okay, beta ji? Yes, sir. Now, please observe. So, on 0th clock pulse, we are considering the state to be 0, 0, 0 on application of 1st, 2nd, 3rd, 4th, 5th, 6th, 7th, 8th. So, on different clock pulses, we can see the different states. Now, please observe. I am interested to check on the first clock pulse. See, Q0 toggles on every clock pulse. Q0 toggles on every clock pulse. Q0 toggles on every clock pulse. Q1 toggles whenever Q0 will go from. Q1 toggles whenever Q0 will go from 0 to 1. That indicates this will go from 0 to 1, 0 to 1, 0 to 1, 0 to 1. So, it means this toggles when it changes 0 to 1. It will remain same from 1 to 0 because there is no clock from 1 to 0. Whenever Q0 changes from 0 to 1, it toggles. Whenever Q1 changes from 0 to 1, Q0 changes from 0 to 1, Q1 toggles. Is it okay? Because the clock appeared onto the flip-flop. And in the same way, if we talk about Q2, then Q2 toggles whenever Q1 changes from 0 to 1. Whenever Q1 changes from 0 to 1. Okay, yes sir. So it toggles. It would remain same until unless again it changes from 0 to 1. Then again it toggles. It can be clearly observed how many number of different states are there. You will not count this state. Never count this as a state before applying clock pulse. Always start counting the states after applying the clock pulses. So 0, 0, 0 is a state, but we are getting onto the 8th clock pulse. Total number of different states are 8. This is your mod 8 down counter. Hoping all of you able to understand this perfectly. Down counter. Hoping all of you able to understand this perfectly. Please let me know by writing in the comment section, Bitaji. Great, sir. We can also see about the frequencies. If we observe the timing diagram, for this circuit, then its timing diagram will become, please observe Bitaji. So we are considering a positive S triggered. Positive S triggered means whenever the clock changes its level from 0 to 1. So these are the positions where the clock would appear onto the circuit. Hoping all of you able to understand up to this part. I am just extending the positions where the clock is changing from 0 to 1 in order to observe the change in the outputs. For a moment, consider zero propagation delay. So on considering zero propagation delay, we all know and we have in mind that what must be the time period of the clock for satisfactory operation in case if the propagation delay is present. So Q0, Q1 and Q2. Initially Q0 is low. It changes on every positive S triggered clock pulse. It changes its level on every positive S triggered clock pulse. Q0, Q1 changes its level whenever the Q0 will be changing from 0 to 1. Q1 toggles when Q0 changes from 0 to 1. Q2 toggles when Q1 changes from 0 to 1. Is it okay? Yes, sir. So it is changing from 0 to 1 on these positions. So it toggles. How many of you able to understand up to this part? Great. Q2 toggles only when Q1 changes from 0 to 1. So Q1 is changing from 0 to 1. These two positions. If you observe, we have initially 0, 0, 0, 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1 and 0, 0, 0. So how many total number of different states we are getting? We are getting total number of 8 states. So this is your mod 8 and why it is called as a down counter. Hoping now all of you able to understand. Is it okay, Bitaji? If we have a clock time period TCLK, then output Q1 will have a time period 2 TCLK and our output Q0. Q1 will have a 4 TCLK and the output will have 8 TCLK. So now we know about the output frequencies as well. Clock frequency, if we know about the clock frequency, FCLK is 1 upon TCLK. So we can observe Q0, Q1 and Q2 as well. 1 upon 2 TCLK, FCLK by 2. In the same way, FCLK by 4 FCLK by 8. Always remember, if we have mod 8 counter, then for a clock frequency FCLK, we get output frequency from final output as FCLK by CLK M for a mod M. For a mod M counter. For a mod 8 counter, it would become FCLK by 8. For a mod M counter, it will become FCLK by M. Hoping all of you able to understand this. Great, sir. So now all of you able to understand the ripple counter. Can I say that all of you now able to understand the ripple counter? For satisfactory operation of the circuitry, your TCLK must be greater than or equals to NTPDFF, where N is the number of flip-flops. Where N is the number of flip-flops. Is it okay, beta ji? Please let me know by writing in the comment section. Hoping all of you now able to understand the ripple counter in a proper way. Is it okay? Great, sir. Can you tell me one question I just wanted to ask you? Okay. One very important, you can just have this. You can check with which, if you are going to connect, then it is going to act as a up or a down counter. Is it okay? Great. Now I am giving you one question. Can you answer this question? Let me take a gate part question if it is available. Okay. Okay, I am creating one question. Please observe. Find the output frequency at output Z shown in figure for clock frequency of 10 megahertz. Okay, you have to tell me 1, 2, 3, 4, 5. You have to tell me the output frequency. We have T flip-flop. All the T are connected with logic level 1. All the T are connected with the logic level 1. Okay. Input clock is given here. Having frequency 10 megahertz. Output of this will going to become the clock of the next, and that too positive is triggered. Also, you have to tell me whether it is a up counter or a down counter. Okay. You have to tell me the output frequency at output Z. From the figure shown below, we have 5 flip-flops and the flip-flops are connected like this. So first is to observe that all the flip-flops are T flip-flop or a JK flip-flop, and the inputs to them is 1, and only one flip-flop is connected to base clock pulse, and the output of one flip-flop is the input of other flip-flop, input clock of next flip-flop, that indicate this is a ripple counter. Is it okay? Yes, sir. So now observe how to identify the LSB. Only one flip-flop with which clock is connected, that will act as a least significant bit. So definitely this is going to be the least significant bit. Yes, sir. If the clock frequency is FCLK, then this will become, we all can see the timing diagram now. You all can see the timing diagram now. On every clock pulse, Q0 get toggles. Yes, sir. The output Q0 is becoming clock to this. And that too as a positive S triggered. That too as a positive S triggered, which indicates 0 to 1. So whenever Q0 is changing from 0 to 1, then Q1 is changing from 0 to 1. That indicate it is a down counter. There is no doubt in this. It is going to be a down counter only, because initially if all 0 0 0, they are becoming 1 1 1 at the same time. So it's a down counter. Next, the output of this flip flop. Okay, I made a mistake here. Kindly connect like this. Again, I make a mistake here. You need to connect like this. Okay. Okay. So output of Q1 will become output Q1 will become I'm changing the color so that it can be properly visible to all of you. Output Q1 will become clock to the next flip-flop. So if output Q1 will making the clock to the next flip-flop, then we all can see that this will be your Q2. And the output frequency will be, if this is FCLK by 2, here we have FCLK by 4. Here we have FCLK by 8. Yes, sir. And the output of this is connected to the clock of this. So FCLK by 8, 16. So output Z frequency of Z will become FCLK by 16. That is 10 megahertz. Megahertz means 10 into 10 to the power of 6 divided by 16. You have to identify in terms of megahertz. So can you tell me in kilohertz? So can you tell me in terms of kilohertz, Pitaji? 62.5 kilohertz. How many of you able to understand this question perfectly? So this kind of questions will be available in this particular topic. Hoping all of you able to understand. Mostly students do the mistake considering this as FCLK by 16, FCLK by 32, but that is not true. You have to observe the clock. Is it okay? So this is your Q4, T4 and Q4 complement. Here you will get FCLK by 32. But since the output frequency we have to examine at output Z, so that will become FCLK by 16. Hoping all of you are able to understand this kind of question now. Great. It's a down counter. All of you can see the down counter. All of you can see the timing diagram of output at any output port. Is it okay? Great. Hoping all of you are able to understand, Betaji. So there is a decoding error. What is the disadvantage of your ripple counter? See, asynchronous counters, we generally design only ripple counter. Because rest of the counters, if we are going with asynchronous, the design will become difficult. And also, it is very challenging because each flip-flop will have different clock. So instead of going with asynchronous, we always prefer to go with synchronous, because synchronous counters are comparatively faster. Now please observe, there is an error due to propagation delay, TPD, of the flip-flop, and which is known as a decoding error or transient state error. Is it okay? Yes, sir. Decoding error can be eliminated by using strobe signal, where the outputs are passed through the AND gate. Okay. Also always remember, In case of in asynchronous counters, in asynchronous counters, clock period of the time period of the clock must be greater than or equals to n TPD FF, where TPD FF is the propagation delay of the flip flops. If we are using strobe signal, then with a strobe signal, because we are using one AND gate, so TCLK needed will be greater than or equals to n TPD FF plus TPD of AND gate. Okay. So always remember this. Hoping all of you able to understand up to this part. Great, sir. Now, to overcome the difficulty of the asynchronous counters, we design synchronous counters. But before moving towards synchronous counter, let's have a non-binary ripple counters as well. So in a non-binary ripple counter, in designing of non-binary ripple counter, we use reset or preset pin. Is it okay? What is reset or preset pin? Please observe. Reset or preset pins are used in ripple counter. Okay. So if we talk about reset or preset pin, this is the pin used to clear the flip-flop state or to set the flip-flop state. It can be a D flip-flop, T flip-flop, JK flip-flop or SR, any flip-flop. There is, along with the flip-flop, we have a pin called clear pin. And it functions absolutely in the same way as we know about the AND gate. So we all have NAND latch. In the NAND latch, if we use one enable pin as well, which can either set or preset QN, so that we are using here as a clear pin. Is it okay? Yes, sir. So internally, what is the function of this clear pin? The function, this is going to enable, which it is going to control the latch of a flip flop. Is it okay? Yes, sir. And how it is going to do, sir? We have a clear pin. Whenever a clear logic level 1 appear onto this pin, whatever data available on QN, it will be resetted. So if clear is high, the data get resetted and QN will become 0. If a bubble is present onto the clear, then it is called as clear bar pin. In a clear bar pin, if we are getting 0, then clear bar will become logic 1. Whatever data on QN, that is resetted to 0. Same circuit, everything remains same. If you are using here NAND, if you are using here NOT gate, then on 0 it will become cleared. And if we are using normal without any NOT gate, then by using 1 it get cleared. Is it okay? Yes, sir. In the same way, we have preset and preset bar. In preset bar, if we have a input pin getting 1, whatever data it is going to set, we all know how to set or reset the latch. Is it okay? So the one pin is to reset and one pin is to set. That is called as preset pin. If the preset pin is 0, then it presetted to 1, that's because preset bar is 1. If preset is 1, then also whatever data at QN is going to preset it to logic level 1. Is it okay? Yes, sir. So now we know about the preset and reset pin. There are two types of preset and reset pin. One is called as a synchronous preset pin. Another one is called as a asynchronous preset or reset pin. In a synchronous preset or reset pins, the reset or preset operation implemented only when the clock appear. It means along with the reset or preset condition, when the clock appear, only then reset or preset happen. It means the reset or preset are being synchronized with the clock. Is it okay? However, in case of asynchronous, In case of asynchronous, if the condition appeared, irrespective whether the clock will appear or not, reset or preset condition occurred. That is what we called. Yes, beta ji, preset, reset, preset. What happened? Reset condition or preset condition? Is it okay? Great. Now, can you tell me, now all of you know about the reset and preset conditions as well? Reset is used to clear the flip-flop and preset is used to set the flip-flop. Reset is used to clear the flip-flop and preset is used to set the flip-flop. Now, let us first discuss about बहुत ज्यादा है यार, ये तो कैसे खबर होगा? Okay, let's have a first discussion onto the non-binary ripple counter, that is BCD counter. See, if we talk about decade counter will have how many number of different states? Sir, I have just joined the first year MCA at NIT Varangal. Beta ji, you have to follow your curriculum. Okay. So the only thing is you have to study your curriculum in a proper way to understand the things. Okay. That will help you a lot. In the first year, you may get digital logics and that you can follow. Now, please observe decade counter. Rest we will discuss. But let me cover, because synchronous counter also I have to cover today only. So first, let us talk about decade counter. If we talk about decade counter, then what is decade? Decade means 10 different states. Decade means 10 different state. Decade means, beta ji, up to this part everything is clear? Great. Now please observe the decade counter. Decade. Okay. We have time. 30 minutes I can cover. Now please observe here. Decade counter. Now please observe here decade counter. Okay, beta ji. Decade counter is one which has 10 different state or 10 distinct state. Okay. No matter what the sequence is, it can be in any sequence. Then the counter is called as decade counter. But if the decade counter counts in a sequence from 0 to 9, it is called as BCD counter. So always remember, all BCD counters are decade counter, but the reverse is not true, because BCD counter will have 10 different state, but in a sequence of 0 to 9 binary. However, a decade counter will have 10 different state in any sequence. So I am considering a decade counter. In a decade counter, we are talking about BCD counter, because all BCD counters are decade counters. All BCD counters are decade counters. Is it okay? Yes, sir. So please observe how to design a BCD counter. I am interested to design a BCD counter. Okay. So how many number of flip-flops are needed for a BCD counter? We all know m is less than or equals to 2 to the power n. So we want 10 states. So how many number of flip-flops are needed? We all can see flip-flops needed must be equals to 4. Is it okay? We can't use half flip-flop. So we need 4 flip-flop. Hoping all of you able to understand up to this part. Great. So I'm using 4 flip-flop. Either you can use JK flip-flop or T flip-flop. So let me show you a JK flip-flop now. JK flip-flop having J equals to 1 and K equals to 1, same as T flip-flop having T equals to 1. Okay, beta ji? Yes, sir. Or you can also represent like this. You can also represent like this. JK11. Both are the same thing. JK11. So JK flip-flop is in a toggle mode. I'm using a negative edge triggering. Negative edge triggering is usually preferred over positive edge triggering because we are getting some extra time at the time of start to stabilize the circuit. Okay. So negative edge triggering, and this will become your LSB because base clock is only applied to one flip-flop, and that will act as a least significant bit. So whenever Q0 changes from 1 to 0, Q1 get toggles. Whenever Q1 changes from 1 to 0, Q2 toggles. Whenever Q2 changes from 1 to 0, then Q3 toggles. So we all know how to mark the LSB and MSB as well. Since we have to design a flip-flop which counts in a sequence from 0 to 9, BCD counter counts in a sequence from 0000 to 1001. Is it okay? Decade counter, when counts in a sequence 000 to 1001, it will be a BCD counter. So we need a clear pin because 000 is also a state needed. In case if 000 is not a state needed, we can go with a preset pin, okay, for some other counter. But presently we have to design a BCD. So I'm going with the preset pin, clear pin. Clear pin is also called as reset, clear or reset pin. This can be represented as CLR, clear, or reset pin. Is it okay? All the clear pins I am going to connect together, and some condition I am going to pass through the AND gate to get the clear operation done. So first of all, I am interested to design up counter. Then only it counts in a sequence from 0 to 9. Is it okay? Yes, sir. So I have designed up counter by using negative S trigger. It is up to you. You can design with a negative or positive S trigger. Next is we want only the states valid from 000 to 1001. So how is it possible to have a states from 0001 to 1001? All of you can observe the up counter. Yes, sir. So we have a clock Q3, Q2, Q1 and Q0. In case if we are talking about 0th clock, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So what you want from 0 to 9 binary will appear. Okay. And the then repetition again happened from 0 to 9 only. The binary of 0 to 9. Then only it is called as a decade counter or a BCD counter. Okay. Yes, sir. So now please observe, since you have connected Q0 flip-flop, this flip-flop with a base clock, so it means output Q0 toggles on every clock pulse. Yes, sir. So output Q0 toggles on every clock pulse. It means if initially we consider 000 onto the 0th clock pulse, it toggles on every clock pulse, on every negative S triggered clock pulse. Is it okay? Yes, sir. Q1 toggles whenever Q0 changes from 1 to 0. So Q1 toggles whenever Q0 changes from 1 to 0. How many of you able to understand up to this part? Great, sir. Then Q2 toggles whenever Q1 changes from 1 to 0. So Q2 toggles whenever Q1 changes from 1 to 0. Yes, sir. Similarly, Q3 toggles whenever Q2 changes from 1 to 0. Q2 changes from 1 to 0. Is it okay? Yes, sir. We want up to this state. On the 10th clock pulse, what state we get as per the arrangement? As per the arrangement, what we get on the 10th clock pulse? On the 10th clock pulse, we would get, on the 10th clock pulse, we would get 1, 0, 1, 0, 1, 0, 1, 0. But you don't want this state to be a stable state. It appear, but you don't want this state to be a stable state. It appear 1, 0, 1, 0 on 10th clock pulse appear, but you don't want this to be a stable state. So for 1, 0, 1, 0, for 1, 0, 1, 0, this is your 1, 0, 1, 0, 10. MSB, LSB, please keep that in your mind. So if I pass this Q3 to this AND gate, this Q3 with this AND gate, and this Q1, if I pass through this AND gate, then this AND gate output will become logic 1 in only one condition, when the binary of 10 would appear. When the binary of 10 appears, then only the AND gate input will become 1, 1. Otherwise, if you observe here, Q2 is 0, Q2 is 0, Q2 is 0. Here Q2 is 0, Q2 is 1, but Q3 is 0. Q3 and Q1, you can observe Q3 is 0, 0, 0. Until unless Q3 is 0, we all can see the AND gate will have output 0, and if the AND gate output is 0, clear operation would not perform, and we have a stable states. We have a stable states at the output. On to the 8th clock pulse, Q2 is high but Q1 is low. On to the 9th clock pulse, Q2 is high but Q1 is low. On to the 10th clock pulse only, first time, this AND gate, both the inputs will become high. So now the output of AND gate will become high, and the clear condition appears. All the flip-flops will reset it. So this state appeared partial state, and finally it stabilizes to 0, 0, 0, 0. So instead of getting 0, 1, 0, 1, it stabilizes to 0, 0, 0, 0. Why? Because clear condition occurred. Clear condition occurred. Soon as the clear condition occurred, it will again 0, 0, 0. And then on to the 11th clock pulse, you will get the binary of 1 now. Then on the 12th clock pulse, you will get the binary of 2 now, and so on. So how many number of different states we have? We have a total number of different states 10. How many of you able to understand, Bitaji, a non-binary ripple counter? How many of you able to understand the non-binary ripple counter as well? Great. And a BCD counter as well? Great. Hoping all of you able to understand the non-binary ripple counter. Is it okay, Bitaji? Can you observe this one? We have this condition. Okay, please observe. The ripple counter shown in the figure is made up of negative S triggered JK flip flop. The signal level at J and K inputs, all flip flops are maintained at logic level 1. So the input to J and K is 1, 1. It means JK flip flops are operating in a toggle mode. Assume all the outputs are cleared prior to applying the clock signal. Modulus of the counter is, you have to identify whether the counter is mod 4 counter, 5 counter, 6 counter, 8 counter. What is the mod of the counter? So it can be clearly observed that negative S triggered means Q0 toggles on every clock pulse. Q1 toggles only when Q0 changes its level from negative S triggered means 1 to 0. So that indicate it is a up counter. How many of you able to understand, beta ji? Great. In the same way, you can observe here, Q2 toggles only when Q1 changes from level from 1 to 0. So it's a up counter. In a up counter, you will get the binary of, it is a up counter. So here I am using clock Q2, Q1, Q0. Okay, yes sir. Now, initial state is not given, so let us consider onto the 0th clock pulse. If the initial state is not given, you can consider it as logic level 0. 1, 2, 3, 4, 5, 6. Okay, yes sir. Now please observe here. What happened on first clock pulse? Binary of 1 would appear. Since this is a NAND gate output is logic 0 only when both the input of NAND gate is logic 1. And because this is a clear bar, so that indicates the clear condition appears only when the NAND gate output is 0. NAND gate output is 0 when both the input of NAND gates are, logic level 1 1, because 1 into 1 1 complement 0. Is it okay? Otherwise, the output of NAND gate is logic level 1. Until unless the output of logic level is not 0, the clear condition would not appear. So it can be clearly observed, the clear condition appear when Q2 is high and Q0 is high. So it means when Q2 and Q0 is high, it's up counter. So binary of 1, binary of 2 and so on. You can observe the first time when Q2 and Q1 is high. Sir, it becomes high onto the binary of 5, 1, 0, 1. Is it okay? Yes, sir. On binary of 3, you will get 0, 1, 1. Again, Q2 is low, so your clear condition would not appear. 4. Again, your Q0 is low, so clear condition would not appear. On the binary condition of 5, the clear condition appeared. Is it okay? Yes, sir. As soon as clear condition appeared, it get cleared. How many of you able to understand? So, soon as the fifth clock appears, the condition, clear condition appears. So we will not get this 1 0 1. Instead of that, we will get 0 0 0 as a state. So how many different state? 1, 2, 3, 4. 0 0 0 is also a state which is counted onto the fifth. We will never count this state 0. We always started after applying the clock pulses. So this is your mod 5 up counter. How many of you able to understand? This is a non-binary ripple counter. Hoping all of you able to understand this concept. Great, sir. Generally, we avoid to use a non-binary ripple. Generally, we avoid the use of asynchronous ripple counters. Is it okay? Yes, sir. So I am giving you one homework. Hoping all of you can go through this homework. A very similar kind of question which we have observed earlier. You can easily do this question and paste your solution onto your Telegram, Varun sir PW. So you can utilize your Telegram group for your group studies as well. Very good question. You must try this one. I am giving you as a homework. This is a gate question. Okay. Please try once. I will discuss tomorrow. But at least first time you should try. These are all clear bars. Okay. And logic level 1 and everything is shown. Wherever the dots are highlighted, only they are the positions where it is connected. Wherever there is no dot, it means it is going like this. Is it okay? Now utilize this as well. So till now we have completed asynchronous ripple counters, and we understand the difficulties with the asynchronous counters. Let's have a discussion onto the synchronous counters. Synchronous counters are very fast and can be designed for any count sequence. The basic difference between asynchronous and synchronous counter is asynchronous counters will have fixed count sequence, maybe up or a down. However, if we talk about synchronous counters, they can be designed for any desired count sequence. They can be designed for any desired count sequence. Is it okay, beta ji? Great. So we'll discuss synchronous counters by tomorrow. Hoping all of you able to understand asynchronous counter by today. Because already the time your watch approaches now. So we'll discuss synchronous counter tomorrow, and day after tomorrow we will move towards the finite state machine. Is it okay? Synchronous counters I am going to discuss by tomorrow. We will see how we can design any desired synchronous counters for any count sequence. Whatever counter you want to design, just imagine and keep the data with you that you want a binary of 0, then binary of 7, then binary of 2, then binary of 3. Tomorrow we are going to discuss about the designing of asynchronous synchronous counters, and after studying synchronous counters you can design any desired synchronous counters. Is it okay? Hoping all of you able to understand synchronous counters now, beta ji. We'll discuss asynchronous counters now. We'll discuss synchronous counters by tomorrow. One small request, please keep these two pages in your copy, okay, so that you will be able to understand and you can easily design the asynchronous and synchronous counters of your desired synchronous counters. Okay, so desired synchronous counter, first of all you have to remember that it can be designed for any count sequence. All the flip-flops are connected with the same all the flip-flops are connected with the same clock. All the flip-flops are connected with the same clock pulse. Is it okay? How to design? Let me discuss the steps so that you can write. By tomorrow we will see the steps detail as well. First, find the number of flip-flops required by the equation m, small m is equals to small m is equals to small m is equals to less than or equals to 2 to the power n, where m is the number of states and n is the number of flip-flops. Choose the type of flip-flop, then draw a state diagram and construct a state table of the required flip-flop. Better to construct a state table of the required flip-flop, then write excitation, construct excitation table, construct excitation table of the selected flip-flop from the state table. I am making it easier. Just you need to construct a state table, then write excitation table. Write excitation table. Okay, just write excitation table, then use K-map to minimize the flip-flop input functions and implement the circuit. Okay, circuit implementation. So we'll discuss these 4 steps, how to use them to design our desired synchronous counter tomorrow. Hoping you have enjoyed the session so far. I have given you 2 homeworks, so please go through the homework and you can check whether your homework is correct or wrong or whatever you are attempting now on your Telegram, that is Varun sir PW. Already the scanner I have shown to you. Once again I just show you the scanner. You will get the PDF of this lecture on my Telegram, as well as for the PDF portion you can go through the description part of the video. Okay, so there also you will also get on pw.live on the free batches. Okay, so thank you everyone, lots of love, good night.